These chapters are not right. The book, it was for the old book, but the chapter, they rearranged the chapters here. So what we do is we take 2 blocks of material are needed, one N and one P. So the N region has many free electrons, right? You understand that? And the P material has many free holes. And the 2 materials are what? Fused together. The point of contact, we refer to this as a P-N junction. At the instant the 2 junctions are formed, or the junction is formed, some electrons jump from the from the N into the P, right? You understand? And then, of course, and as soon as that happens, so these electrons recombine with holes. These leave the holes in the N region. This causes the P-N junction to become electrically neutral. The area on both sides of the junction become depleted of majority carriers, and this is what we call the depletion region. So this is what happens. So we have no free carriers inside the depletion region. But right on this side right here, we'll form ions, and on that side, we'll form ions now, right? I understand. This happens as soon as the P-N junction is made. You understand? Now what's going to happen is they're going to recombine until the depletion region gets wide enough so the electrons cannot migrate across it anymore. Because that guy's depleted of majority carriers, right? There's no free holes in the depletion region, and there's no free electrons in the depletion. This is what we call a P-N junction. Technically, this guy becomes a electronic component called a diode. Have you ever heard of that term before? Now, what this does is it sets up a barrier potential. And the way the barrier potential, and you can literally measure this. And so this forms this. So the P region. So we end up with this symbol right here. And then we put a bar right there. And then we come out. And this is the symbol for the P-N junction. So when we have a P-N junction, even with transistors, we'll draw the arrow. We just leave off the flat spot. Now, the current flow through the device is going to be, we call this guy right here, we call the N material, has a name. We call this the cathode. E, and then we call this guy here the anode. So the term anode is representing the positive region, the P material, and the cathode is the term we use for the. This came up through vacuum tubes. So a vacuum tube consisted of 2 parts. The cathode was a device that was that when we heated it gave up. When we heated it, so vacuum tubes had to create electrons from heat. So they had one material here that when you heated it, it would release what we call a cloud of electrons. So the cathode was the provider of electrons, and then we would come over this guy, and we had a unit called the plate, which was the anode that we would charge to a big high potential. So when we heated up the cathode, it would emit all these little negative charges, and then what would happen? Well, what would that'd be sucked toward the what? Toward the positive potential. And then what we'd do is we'd make it go through these little screen wires that we call a grid. And we'd come over here, we would control the negative potential on the grid. So what would happen is that if you got it up high enough, you wouldn't let the electrons get through to the anode. If you started making it less negative, then you could control the current flow through that. So we can control the current flow with the grid. And so we can make it amplify signals, right? You understand? So I got to take a little old tiny signal and put it right here, because the grid was right on top of the cathode, and the anode was way up here. And with a very, very small grid voltage, not a current, a voltage, we can control a lot of current between the cathode and the anode, which means I could take a real small current and get a watt out, a large current out. And so when they came up with the cathode and the anode, this came apart because the cathode handles the electrons, and then it's going to try to move through the anode, right? That makes sense. And these terms came from tubes. And we can identify it. I'll show you how to identify it on these diodes that we get. But everybody okay? So this is going to set up a barrier potential. And the barrier potential is for silicon is going to be around 0.7 of a volt. Some books teach 10. Some books teach 0.7. Now you can't get any work out of this because it's got a high resistance, right? You understand? But if we got an extremely high resistance meter, we can measure this. We can literally measure this. So silicon, the barrier potential is around what? 0.7. Some books teach 0.6. Who's right? And germanium is around 0.3, 300 millivolts. And that's because when we do this, we create those ions, right? And as soon as I create those ions, then I create electrical potential. And we can measure it. And that's one of the ways we tell what type of diode it is that if I measure it across and it measures 6, 7/10 around there, I know it's a silicon diode. If I measure it and it's 2, 3, like that chance, I know it's a watt. I know it's your germanium. So that's one of the reasons we can tell. And we forward bias these things, we set them up. We'll talk about bias in a second. But that's the symbol. This is supposed to be filled in for the symbol, by the way. But most people don't when they draw them because it just takes a little while. So this bar represents the what? Cathode, but it actually represents the N material. And then the arrowhead, this side of the arrowhead represents the P material. And that's our symbol. Of course, it would be a lot easier to draw. So we have this thing right here, which would be very complicated, but I can represent a P in junction with a symbol. Transistors we'll get into later on, they'll have an arrowhead on it too. And what that does is it identifies the N material. The presence of a positive and negative ion on opposite sides of the junction creates a barrier across the depletion region. The barrier voltage, this is given as VF on the data sheets. So normally what we do is we use what we call rule of thumbs. So 0.7 of a volt is what we use. The actual barrier voltage actually varies. So with current flow through it, which should make sense. So 0.7 we use for about 0.7 for silicon and about 0.3 for germanium. Forward bias, it's going to prohibit it. And can you see what's going to happen? So if I come over here on that diode, okay, so here's my P in junction. And of course, what do we have right here? We have a barrier. And let's say, and this is P, and then this right here is N, right? You understand? Well, what's going to happen if I come over here and put a negative toward that side and a positive toward that side? Well, what this guy here is going to suck electrons this way. And what's it going to cause the barrier to do? This is going to suck holes this way. What's it going to cause the barrier to do? The barrier is going to expand. Because what we're doing is we're pulling the holes out of this side, we're pulling the electrons out of that side, and the barrier just gets what? Just gets bigger. Y'all understand that? And of course, the bigger the barrier, the more resistance the thing has. Now, if I come over here and change this, and we'll have to put a resistor in series with it, because if I don't, it'll burn my diode up. So if I had two batteries hooked up series opposing, oops, I think I can get it. And y'all studied that in DC, right? I think in intro, series opposing, series 80. So basically what we're doing is we're fixing to hook this thing up series opposing. And this right here is a variable power supply. This guy right here is fixed at 0.7 of a volt. And I come up here and do this. Well, I'm sitting down here at 0.3, then basically this guy can't provide current, but this guy can't push against it, right? You understand that? So how much current flow would we have? Well, we're not going to have any if this was a diode. Now, in real life, we would have a little bit. If these were two real batteries, we would be pushing from left to right. But this is a battery, this is not. So the diode cannot push, right? You understand? So I come up here and I get this at at 0.8 volts. Now we're going to conduct that way. As soon as I conduct that way, anything above 0.7 of a volt, that's a short circuit. That's a straight piece of wire. Y'all understand that? So that means what I would have to do is I would have to have a resistor right there. So when we come over here and put this potential like this on there, so what I'm going to do is I've got my P in junction. This is N, this is P, and I'm going to come over here. I'm going to have a resistor, because as soon as I exceed that 0.7 of a volt, everything above that's a short circuit, right? Now it'll go through the resistor. And I'm going to come over here and put the battery, and I'm going to put it right here. So I'm putting the negative toward the N and the positive toward the P. Well, this negative is going to push electrons toward here. This positive is going to push holes toward there. And so these holes are going to start, these electrons are going to drop into the holes are going to fill with electrons. So what happens is now we have over in the N material, I have electron flow. Over in the P material, I have hole flow, and right at the junction they start combining. And what limits the current, of course, would be the resistor. If I didn't have that resistor in there, as soon as we exceeded that 0.7 of a volt, this guy would avalanche. So if I forward bias, we call this forward bias. So to forward bias, I put the negative terminal toward the cathode, and I put the positive terminal up toward the what? Toward the anode. As soon as that thing exceeds barrier potential, it's going to act just like a closed switch. If I reverse bias it, I'm going to put the positive toward the cathode, I'm going to put the negative toward the anode, and it acts like an open switch. I didn't say it is, right? I said it what? Acts like. So even when the diode is forward biased, there's going to be some minority current flow in the opposite direction. When we reverse bias it, this is not an open switch. There is a path for current to get through there. It's just that that current's going to be controlled by what we call whole or minority carrier flow. And it's going to be controlled by temperature. So that's why it's not, we don't worry about much about what happens when we forward bias, because we're only dealing with 0.7 of a volt. But reverse bias, we're really concerned with temperature. We call it leakage current. And they'll tell you, that'll be part of your data sheets. They'll tell you the leakage current in the function. So now we got something. Now we got a switch that I can control electronically. So instead of me going up there and doing what? Flipping the switch, we can control this guy electronically. Forward bias, it acts like a what? Closed switch. Reverse bias, it acts like a open switch. So think what happens if we put AC on this thing. One polarity is going to forward bias it. One polarity is going to reverse bias it. Forward, reverse, forward, reverse. So what we'll do is we'll only let one of the alternations get through. One of them's going to be what? Blocked. The other one is going to be passed. And now we're going to have current flowing in one direction. Even though it only looks like this, that's still DC because it never changes direction. We'll look later on as we get along. So diodes, so understand what's happening. So if I put this on a diode, and then I come over here and put this on a diode, well, when it goes positive, it would be forward bias. When it goes negative, it would be reverse bias, right? You understand? So one way it's going to let what? Current goes through. The other way it's going to block it. And then we'll learn out later on how we can get that other alternation up here. And then we'll start moving more toward DC. So this is one of our main uses for a diode, so one of the main categories of diodes are called rectifier diodes. Y'all heard the term rectifier before? What is it? What does rectifiers do? If you're in alternators, so your alternator generates AC, but your car runs off of what? DC. So inside there is a bunch of diodes. They call it a rectifier assembly that takes your what? Takes the AC coming off your generator, your alternator, and converts it into. When you get into DC machineries, and they did this up in the, and I didn't argue with him. He wanted to call an AC generator an alternator, and that's not true. The only time we really use the term alternators is if you're in cars. And the problem they have is the first generators they put on cars were what? They were DC generators. And then they figured out, when the diode came along, what did they figure out they could do? They could take AC and convert it into what? DC. And AC generators are a lot cheaper than DC generators for the same power. But you have all these mechanics out there that have been calling the dang things generators for years and years and years. And then they came out with an AC generator, they got what? Totally confused. So they changed the name. So they say this car has an alternator, this car has a generator. So the alternator term was used for mechanics, or auto mechanics. In the trade, we call them AC generators and we call them DC generators. So if you get out in an industrial application, they won't call it an alternator, they'll call it an AC generator. Because that's what they do, they generate electricity. So that's a little pet peeve. So this guy here was supposed to be, and he corrected somebody because they called it might have been me, when I called it an AC generator. And he said, oh, it's an alternator. It's an alternator. They got where they wouldn't ask me questions anyways. Let's skip over. So everybody okay? So this is all we'll do. We'll probably have to review a little bit. So I might let one of y'all teach it to the people that's not here. Anybody want to do that?